we need to prime Heron's fountain. So we're gonna start by pouring water in the top. And we need to fill it until it fills up this whole bottom until it gets to here. Now that it is filled on the bottom, we're going to flip it. Dump out the excess. And then we're gonna have it fill up the bottom bottle. All right. Now the bottom bottle is filled. We're gonna flip it back over. Now Heron's fountain is primed and ready to be tested.
So to build this fountain, you need two water bottles that are the exact same size, and one bigger water bottles for the fountain part, so the water doesn't get out. So what I did was I glue the two caps together into like this, and I cut the another water bottles as the base, and I glued that too. And then I made two holes on this cap, and then two holes on this part, and I built a straw. The blue one is from here to here, and the red straw from here to here, and the green from here to here.
For Heron's fountain, it is a hydraulic fountain that is run based off of water and pressure in the system. So when we start, you start by pouring water at the top, and there's this blue straw that is connected from this bottle cap here, and it goes all the way down to the bottom of the second bottle. And then in here there's a red straw that goes from the upper part of this bottle to the top part of this bottle. And then there's a green straw that goes from around this part of this bottle, and it goes up to here where the fountain will come out of. So how it works, pour the water in here. Water drains down into the bottom, it rises and pushes the pressure up with the air into this bottle here, up into this part, which is then going to push the water that is in this part of the system up through the green straw and out through the top, and that's how Heron's fountain works.
We realized that the smaller straw diameter affects the height and the time the fountain will run. This fountain, the time was 3.5 minutes, and the height was 0.5 inches. For this one, the time was 15 to 20 seconds, and it was 1.4 inches. So yeah, this one was much longer. I mean, no, it took longer time, and then the height was very short compared to this one. Yeah.
For this project, we used Bernoulli's equation to calculate the pressure that's in the system, given from the height that we received from our data collection. And we originally thought that using the conservation of energy equations, that might have an effect on the duration or the height of it based off the diameter of the straws, because mass flow rate includes the diameter of the pipe, or in this case a straw, but it only affected the mass flow rate. It didn't really change anything within the equation or Bernoulli's equation. So the height difference wasn't really anything that had to do with it. The diameter, the duration was the only thing that really changed in a way that it lasted longer. We did find that there were a few setbacks with our design.
So the problem we had with this design is that the seal wasn't tight enough where it caused water leaks, which could affect our data. So yeah, that's pretty much it. Just the leaks. We didn't make a very good seal. So that's why you have this duct tape around to try to make it
Better.
yeah, try to make it better, less leak on the water.
And of course, frictional effects within the straw could also affect the speed and velocity of it. We did find that with this system that the velocity and the flow rate that the water traveled through the blue straw was faster than the water was coming out of the fountain. So that just seemed to be what was observed of why it didn't last as long. So that was kind of our takeaway from it. And yeah, Heron's fountain.